Hello everyone. Good evening all of you. We'll be starting our session in just 2 minutes. Let all the people join our live session. So we'll be starting the class after that. Just 2 minutes I'll take, and then I'll be starting the class. Hi Mahesh. Hello everyone. Hi. Good evening. Yeah, I hope all of you have seen my last live session, which was about the flexural design of shear wall using ETABS and the manual approach, because this boundary element design is related to that part. So if you have not seen this, please do watch the previous session also, so that you can get a little bit idea about how we design shear wall in ETABS and also um, manually. Okay, because everything is interconnected, because this boundary element is a part of shear wall, and also we need to do the flexural design for the middle part, or you can say for the wave portion. So yeah, we need to see both the things actually, otherwise it will be very messy for you, or maybe you will get confused how the things are going on. So yeah, if you are watching this live session, so I do recommend to watch the previous session also. I hope I am audible to everyone. Hello, please let me know whether I am audible or not. Hello. Okay, fine. So please share this live to all of your colleagues and friends, so that we can get more uh, viewers to our live session. It will be very good, so that more people can get to learn about these things. Please share. Okay, so I think we should start because it is already 6:38. So we'll see uh, if some people are joining after that. Yeah, so we have 9 members. So yeah, I'm going to start the session now. Let me just. So today, the topic that we'll be covering is boundary element design, right? Boundary element design. Now, this boundary element design, this particular topic is it was on demand, and very most of the people asked me to create a separate or create a live session or maybe a video regarding this particular topic. uh, you can see there are different tutorials, there are different sessions where people used to show you how you can design the boundary element in ETABS, how it is showing the result. But the thing is, we need to understand the real concept behind the boundary. Okay, so let's start with the basic concept. I'll take hardly 5 to 10 minutes to explain the concept because it is very easy. Then after that, I'll jump back to ETABS, and from the ETABS result, we will interpret the result using our manual method. Okay, so this will be the total workflow for today's session. So first of all, I'll explain what actually boundary element is. So suppose this is my shear wall, right? This is my shear wall, and here it is fixed. Here it is fixed. Okay. So whenever there is a force from any lateral direction, right? Because we provide shear walls mainly to resist the lateral forces, and these are the lateral force resisting elements or members, you can say. So whenever we have a lateral force, suppose force X, okay, maybe this is earthquake force or any lateral force. So in that case, what will happen? There will be a displacement of the total structure and the shear wall as well. So the shear wall will be displacing like this, right? So when it is displacing like this direction, it will create a moment capacity about the axis which is perpendicular to this particular face, right? So the moment will be like this. This is what the measure moment is. That means if this is the section of the shear wall, and here we have got one axis, let me just make it a bit thinner to the line. Suppose this is my shear wall. This particular thing I have already explained in my previous lesson. So suppose this is my one axis, this is the another axis, right? So as the force is coming from this particular side, okay, so what will happen? The shear wall will displace in this direction. So let me name it 2 and let me name it 3. So as it is moving along this direction, the moment will be created, or the moment capacity will be generated along about this particular axis, which is our 3 axis. That's why this 3 axis is nothing but our major axis, as I have explained in our previous lesson or previous session. Okay, so now we have designed for this particular moment, or we have designed for this particular moment capacity. Okay, now what is the concept of boundary element? Why we need this boundary element? See, uh, whenever we have this particular action or displacement, you can say like this. So what will happen? What will happen? If you see, if I divide this shear wall somewhere here, maybe, and somewhere here. So obviously, as the force is coming along this direction, you can see this particular face, this face is under compression, and this particular face is under tension. Okay, this particular face is under compression and the opposite one is under tension. After that, we do have the axial load also, which is our PU. So we have this force due to which we have tension in this face and we have compression in this face. Along with that, we have the axial load PU. So ultimately, what is the scenario? Ultimately, what is the scenario? If you see here, what are the forces, net forces we have? If this is my shear wall, suppose this particular region is under compression and this particular region is under tension, because these are the extreme fibers, right? This is the extreme fibers. These two faces, these are the extreme fibers, or you can say extreme ends of the shear bar. Okay. So these extreme fibers will undergo compression and tension. Okay. The force, from which direction the force is coming, it will be under tension. The opposite direction will be under compression. So here we have the PU, and this direction we have tension. Again, this direction we have compression. So what will be the net force here for this particular area? For this particular area, the net force will be PU plus tension. Here it will be PU plus compression. Now try to understand the direction of the force. Try to understand the direction of the force. Here PU and T, they are opposite to each other. So if we add these two, obviously the total force, the net force is going to be reduced. But here this PU and the compressive force, or you can say the compression is not force, the compression is in the same direction, right? PU and both are in downwards direction. So here the net force will be more. I hope it is clear to all of you. Here the PU, suppose I have divided this PU, so PU1, PU2 and PU3. PU in the area of this wave, PU in the left extreme fiber, PU in the right extreme fiber. Okay, so in the left extreme fiber, if the force is coming from this direction, it will go under tension, and as the PU, that means the axial force on this particular region, is opposite to the tension, so what will happen? The net force will reduce, because it will be the difference between these two. Though we have the plus symbol, but here we will have, as it is opposite direction, the T will be minus T. Okay, and here the PU and the C is in the same direction. That's why the net force will be more. I hope this concept is clear to all of you. Okay, Mr. Srinivas, we will talk about safe afterwards. Okay, let us finish this session. After that, at the end of the session, we will talk about those things. Okay, so here we have this concept. That means the total PU, the total axial force, will be divided to different areas. One is the mid portion, this mid portion, and here these two ends, these two extreme ends. Now what do you understand from this? From this you will understand that this particular region, if I draw a plan of this shear wall, okay, so this particular region and this particular region will be under stress. Here it will be, in case of the first one, it will be tensile stress, and in case of second one, it will be compressive stress. Okay, so the code says IS 13920. If I say IS 13920, okay, IS 13920, if you see the clause number 10.4.1, I guess. Let me see once. It is in 10.4.1. okay, right. So 10.4.1, if you see, it says that if this compressive or tensile stress, the total stress, okay, if the stress is greater than 0.2 FCK, then we cannot provide the same reinforcement that we have provided in the mid part of the shear wall. Okay, so the mid part of the shear wall. So in that case, if the stress is crossing the 0.2 FCK limit, in that case we need to design these areas separately with higher reinforcement. Okay, so these particular regions which are having higher stress, tensile or compressive are called our boundary elements. Are called our boundary elements. Now these boundary elements can be designed. These boundary elements can be designed as column. Specifically, if I say, so you can design it as short column, and it is written, if you see, it is written in IS. I'll show you. Let me show you, then I'll write it here. If I go to IS 13920, as I have said, you can see here the 10.4.1. Okay, keep patience, please stay with us, because I will be showing you how you can check in the section designer also in ETABS. Okay, so today the session will be a bit longer because I will be explaining very important topics today. Okay, so if you see here 10.4.1, here you can see this line, that when the extreme fiber, the compressive stress in the wall exceeds 0.2 FCK due to factored gravity loads. Okay, due to factored gravity loads, in that case, what we need to do, the boundary elements may be discontinued at, okay, not this one, but says, okay, from here the boundary elements shall be provided along the vertical boundaries of wall when the extreme fiber compressive stress in the wall exceeds 0.2 FCK due to factored gravity loads. Okay, so due to factored gravity loads, or due to factored loads, if this the stress is crossing 0.2 FCK, in that case, what you need to do, you need to design it as boundary elements. Which thing? The extreme fibers. Okay, so now the 10.3, if you see the 10.2, I guess 10.4.2, it says a boundary element shall have adequate axial load carrying capacity assuming short column action, so as to enable it to carry axial compression arising from the factored gravity load and the lateral seismic shaking effects. I hope it is clear to all of you. It asks us to, sorry, I hope it is clear to all of you. It is saying that what we need to do, these boundary elements need to be designed, as short column. Okay, these boundary elements need to be designed as short column in order to resist the gravity load and as well as the effect of seismic shaking, Okay, so you can understand it is written in the IS 13920, clause number 10.4.2. Okay, this is page number 16, that the boundary elements, whenever we got this criteria 0.2 FCK, it is crossing the limit. In that case, we need to consider that this area is boundary element, and here we need to design this boundary element as a column, specifically as short column. Okay, now to design the short column, just let me write it here so that we'll find it easy to understand. So where it is, okay, so it is written in IS 13920, clause 10.4.2, right? 10.4.2. So what it says, that we need to design the boundary elements as short column. Okay, now okay, we have got the idea how we're gonna design. So how, from which formula or from which method you are using for designing the short column? Obviously the method given in the IS 456. Okay, if I go to IS 456 2000, clause 39.3. okay, clause 39.3. so there you will find the formula for short column design, which is PU is equal to 0.4 FCK into AC, I guess, let me see, yeah, plus 0.67 FY into AS, okay, AAC. Okay, So what is this formula? This is the formula for designing the uh, short column. Okay, now okay, we have got this formula. I'll show you also in IS 456. Now the IS 13920, if you go to IS 13920, again the same page number 16, and we have this clause number 10.4.3. It says the vertical reinforcement in the boundary element shall not less than 0.8%, obviously, like our column, and not greater than 6%. Fine. The practical upper limit would be 4%. Okay, fine, no problem. Then we have another option here, another written here. Let me see one second where it is. Give me one second. Reinforcement in the boundary element shall not be less than 0.8%. No, not here, not here. Just give me one second. Let me see where it is written. I forgot the area. Yeah, here only. I've not seen. Yeah, 10.4.2.1. 10.4.2.1, it is written that the load factor of gravity load shall be taken as 0.8 if the gravity load gives higher axial compressive strength of the boundary element. So what it says that whatever load we are considering, so it needs to be exactly, it needs to be reduced. Okay, so the column design formula, we have this PU is equal to 0.4 FCKC plus 0.67 FY AST. In that case, what we need to do, we need to reduce it, or we need to reduce the effect using this 0.8 factor. So it is not required to give you the factor to your load cases and again analyze your model. You can directly use this load factor to the formula, so automatically it will get reduced, right? So you do not have to make it again in the mathematical model and change the load factors, because you will be designing everything. So in that case, again separately you need to, right? So it will be time consuming. So there is no need of doing that. So what you can do, the best process is, you can just multiply for the shear wall. You can just multiply 0.8 here with the total formula. So we are not considering the 100%, we'll be considering this 0.8 factor. That means maybe you can say 80%. That case. Okay. So I won't say 80%, it is 0.8 times, not one time. One time means we are considering 100% of the effect. Okay. So here, where it is written, this reduction factor, it is written in IS 13920. I was a bit confused about whether it is 10.4.3 or something somewhere else, but it was in IS 13920 clause, because these clauses, these are very important. This clause 10.4.2.1, right? So we cannot, it is not like appropriate to do anything by ourselves, right? It should be written somewhere or approved from somewhere, right? So there, all this process are approved or it is written in the IS 13920. So we will be following this method to design our boundary. Now, what are the steps? What are the steps? What we need to do first? First, we need to check whether the stress that we are getting in our boundary element or in the shear wall, whether it is crossing 0.2 FCK or not. Okay, so how to find this? How to do that? How to do that? Stress. Can anyone tell me how to find this? The stress, the extreme fiber. So obviously it will be stress, the compressive stress. Okay, so the stress equal to, we have the formula PU by A. Let me just remove this. we have the formula PU by A plus MU. Now, in this case, in case of the design of boundary elements, we will be considering only the major axis moment. Okay, only the major axis moment. So here it will be MU33 because this major axis moment is the major moment, or you can say the moment that is governing, right? In the previous lesson also we have seen that the minor axis moment is very less. Okay, so here we'll be considering the major axis moment divided by the Z. Now what is Z? What is Z? Can you tell me what is Z? Z is nothing but the section modulus. Z is nothing but the section modulus. Now about this Z, if you want to find, see, this is the methods, or this is the process we are going to follow. We are going to find, right? So here to find this value, we have the PU. We'll be getting from this from ETABS. Okay, because everything I'm connecting to ETABS because we will be doing it in ETABS, and from the ETABS result, if you see, ETABS doesn't give us the AST value. So from the ETABS result, how we gonna find the AST or the reinforcement for the boundary element? Here I'm going to show you right now. Okay, so we have got the PU, we have got the area of the shear wall. Okay, we have got the major axis moment. Now, how to find this Z? The formula for the Z is I by Y. I is nothing but the second moment of inertia, or you can say the moment of inertia, and Y is nothing but the distance from the neutral axis. Distance of what? Distance of this extreme fibers. Distance of the extreme fibers. Okay, so to find this I, suppose this is a rectangular shear wall. Rectangular shear wall. In that case, you can easily make it BD cube by 12. You can easily make it BD cube by 12. Now, sometimes what happens, if you are a practicing engineer, you will know this, that in previous days, people used to increase this particular area wherever we are getting higher stress. So what we used to do, they used to increase the size of this particular. Even this practice is still there nowadays also. So the shear wall will be looking like this, like this. Okay, because as we have the higher, more area, the stress will be reduced here. Okay, stress will be reduced here. So in that case, suppose we are not increasing it, but still we need to consider both the cases. Maybe what we will do, we will provide more reinforcement at the end, or we will be increasing the total size of the shear wall, or maybe as we are having higher reinforcement at this end, you can increase the size of this particular area also. This particular area where we are getting this boundary element, or you can say the higher stress, compressive stress or tensile stress. Okay, so in that case, we need to find the I value. So this I is for the rectangular sections. Rectangular sections. Okay, so in such cases, this is the I section. You can see this is the I section. Okay, this is the I section. Now, in case of I section, what we need to use? See, we need to find one particular method so that even we have a rectangular section, then also it will find the result. Even if we have a I section or section like this, then also we will be getting the moment of inertia. Okay, so because what I am saying, you can create an Excel sheet or maybe a sheet in the MathCAD, or you get a sheet in the MATLAB also. So this is the process you just have to follow. Okay, that's why I am telling you one particular method or one particular process using which you can find the moment of inertia for both the cases, maybe rectangular or maybe this kind of I section, or you can say here we used to provide a bulb like this. Okay, so in that case, what you can do, we can follow the method which is parallaxis theorem. What parallaxis theorem says? We have this shear wall. So according to the parallaxis theorem, what is the formula? The formula is I, maybe suppose this is my section, right? This is not major axis. About this we are going to find the moment, moment of inertia. Suppose xx. So Ixx will be BD cube by 12 plus AH square. Okay, so we need to find the Ixx for this. We can divide this particular, the total shear wall in 3 parts. Here we have one part, from here we have the second part, and from here we have the third part. If it is a rectangular section, it will be totally BD cube by 12. But here we have this B1, D1, we have here also B1, B2, you can say, and D2, and here also we have B3 and D3. So 3 sections we need to find, and we need to make it cumulative. So to find the Ixx, or you can say to find the moment of inertia about this axis for this particular 1, 2 and 3. The first section, what we need to do? First of all, we need to find the BD cube by 12, then plus AH square. Now what is A? A is the area of this particular section, and H is nothing but the distance between the main axis about which we are going to find the moment of inertia to the neutral axis. You can say the neutral axis of the whole section to the neutral axis of the section for which we are going to find the Ixx. So this is our H for the case of first case. So this is how we can find the moment of inertia for total shear wall. Right now, if you do not have this box, so we'll be having a rectangular section. In that case, also we have the similar B and D. Okay, so ultimately you are going to get the same result only as will be getting in case of BD cube by 12. Okay, if you have a rectangular section. So use this method to find out the moment of inertia, so that in case you have a higher section here at the ends, you will be getting the moment of inertia properly. Okay, otherwise you need to create again a different sheet or different calculation sheet for this. Okay, so yeah, we have seen how we're gonna find the I value, and Y is nothing but the extreme fiber distance from the neutral axis. Okay, what are the thing? Okay, so after that we will be getting the stress. Now if the stress is greater than 0.2 FCK, so we can understand that we need to design this extreme ends as boundary elements. Okay, so we have got this. After that we need to go for the design. Now in case of design, you will see that the total axial force which is coming on the shear wall, it is getting distributed to the boundary elements. So getting distributed to the boundary elements and to the wave portion or the mid portion of the shear wall. So here you can say it is the main PU, and it is getting distributed to PU1, PU2, PU3 like this. Okay, so we need to find what is the net force here, because we need to find the tension and the compression here. So what is the net compressive force or compressive stress here for the first section, and what is the net compressive force for the second section? How we can find this? First of all, we need to find the total moment capacity, or the total moment for the total shear wall, and we need to deduct the moment capacity of this particular wave. Then only we will be finding the moment capacity of this boundary element 1 and boundary element 2. Right? So after that we can go for the design of the boundary elements using the short column method. I hope this total theoretical concept is clear to all of you. So now we will be going forward for the ETABS model, and I have actually, as I have explained in the previous video, I have used one Excel sheet created by my very close sir, Siddiqui sir. So today also Siddiqui sir helped me in this to create this video, so that the calculation part, whatever I have showed here, what are the calculations, this calculation part will be easy for me to show you here, because it will take more time to calculate again, repeat the design. Okay, so that's why Siddiqui sir have created one Excel sheet using these formulas, so that if there are some suppose our design is failing, so what you need to do, again redesign. So this method, if I do here using like by hand, what will happen, again and again we need to repeat. So in Excel sheet it will be very easy, just we just have to change the value and we can check easily. Okay, so that's why I'm using the Excel sheet created by Siddiqui sir, and I'm thankful to him for this, to giving me this Excel sheet to use. Okay, so you guys can also create make the Excel sheets using these formulas. All the formulas are there in the IS 13920 and IS 456. Okay, and the total process I am showing you how we can go for it. Please don't ask, and again it's a very kind request to all of you, please don't ask for the Excel sheets, because I do not provide the Excel sheets to anyone. I'm showing you the total process. You can create by yourself. You have any issue, you can join our Telegram group. You'll find the link in the description. So join our Telegram group. If you are finding any issue creating this Excel sheets or any calculation sheet, do ask me there. Do ask, like put the question there in the group. So there are so many people present in the group. They can answer you. Even I can answer you directly. Okay. So it will be a better approach. Okay. So let's go to ETABS model now. We have this ETABS model, and here we have the Excel sheet. The similar Excel sheet, if you have seen the last session about the flexural design of shear walls, so in that case also I have used a similar Excel sheet. Here also I am using this Excel sheet so that we can make the work easy for us now. Okay, so let me choose any shear wall from here, maybe the previous one that we have done in the last session, maybe this one. I'll make it all stories. I'll select this. Okay, so right click and show selected objects only. Okay, so this is the shear wall that I'm going to design, and I'm going to design the boundary element for this. Okay, so now I'll select this. I'll go to, already this is analyzed and this is designed as per the actual easy process, the day-to-day process that we are used to use for the design of the shear wall. Okay, just take the load combinations and run the design analysis. Over. Now we need to check the design results and we need to go for designing the boundary. For that, what I'll do, I'll go here and the design preferences and maybe display design info, and I'll check maybe PR longitudinal reinforcing. Okay, so this is the reinforcement we are getting. So people used to show you like this. Okay, now how are you going to understand what is this, like whether we need the boundary element or not? Okay, so if you right click here, you can see it is at the end of this shear wall result. You can see the stress limit 7 MPa, means Newton per mm square, and the compressive stress that we are getting. So obviously this is more than 7. How you have got 7? How you have got 7? Obviously the method is 0.2 FCK. Okay, how we have got 0.2 FCK? 0.2 FCK means 0.2. Here in our case the FCK is 35. So it will be 70. So 7.0 Newton per mm square. Here you are getting this limit 7. But in our case, due to the axial load and the moments, we are getting the compressive stress for the boundary elements, which is this, maybe 12.81, 12, 14.59, 13.33 for different regions. You can see top left, top right, bottom left, bottom right. Okay, that means here it is the shear wall. Here it is the shear wall. So this is my top left, bottom left, top right, bottom right. Okay, so this is how it is to consider actually in ETABS. So what we need to do, we need to find the maximum. Just give me 1 second. Okay, so sorry. So here we need to find one particular value, maybe the maximum one. So you can use, see here, if I am taking this moment, you can say that this is the maximum one. In that case, here what is the moment is less, right? So what we need to do, we need to consider where we have the axial force also and the moment also, because this moment is also governing, right, the major axis moment. So here what I'll do, I'll consider this one, because this major axis moment is the main governing thing for our case. Okay, so here the major axis moment is 2155.959 1959, right? And along with that we have this axial force. Okay, so let me just write somewhere what are the values. Okay, no need, I can write directly from here only. So let me show you. So this is the PU value. What we need to find, the process PU by A, MU by Z, right? So if you see here, you just have to put the PU value, which is 4512, right? 4512. Then we have the factored moment. So for our case, it is 2155. Let me write it specifically. 4152. Sorry, 4152.8599. Okay, 8599. Now the moment is 2155.1959. So 1959. Let me give here. So length of the shear wall, if you see here at the top in the result, it is already given length and thickness of the shear wall. Let me minimize. Okay, so the length is 2310 in our case, 2310. So why we need these values? Because he has created like this. Okay, we need to find the area, right? So for that we need the length and thickness of the shear wall, obviously. So this is totally up to you. What are the things you need to keep first, and you need to uh, make the formulas by yourself using your method. Okay, here you do not have to follow the same maybe the same thing. You can create by yourself. So let me make it to 300. You just have to understand what are the things we need to find the result, and then you can go for it. You can go for creating your sheet by yourself, or maybe you can design manually also. So length of boundary element, what is this? Length of boundary element. See here, the length of boundary element is given in the ETABS, so we'll be giving here 450. Width of boundary element, obviously in our case we are not considering this bulb, or we are not considering this extra area first initially, because ETABS is already given for here. Okay, if it is failing, it will not show here, right? So without this extra area also, we can go for 300 mm thickness only, what the thickness of our shear wall. So in that case, we do not have this particular extra section. Fine. We will find, we'll see if the reinforcement is more, we will increase the size, we will increase the thickness and the length of the shear wall also. Sorry, the length of the boundary element also. Now the grade of concrete, here for the shear we have considered 35 Newton per mm square. Grade of steel is 500. Okay, fine. Okay, the reinforcement ratio for the web means this middle part of the shear wall. You will find where? Here. In the previous lesson we have considered this particular reinforcement ratio 0.00097, that is 97%. Sorry, 0.97%. So here it is already given. Actually, it was used in the previous session. So 0.0097, you can see we have taken the maximum one from the flexural design. Fine. So from here, the next step, the first step, what we need to find, as I have explained here, the first step we need to find the stress PU by A plus MU3 by Z. If you see here, we have the formula PU by A plus minus MU3 by Z. Plus minus means minus will be the minimum, and if you plus, it will be the maximum stress. So we do not need the minimum stress, we just need the maximum one only. Here it is given, you can create. Okay, here we have Z. Z is nothing but I by Y. Okay, as it is a rectangular shape in our case, so here the y, in most of the cases we will be having rectangular only shear wall, right? So in that case, obviously the y value will be half of the this one, the total length. So LSW by 2, you can see from the major axis to the distance of the extreme fibers. Okay, so it is LSW by 2. So this is how. Now how to find this I? Here we have two boundary elements, right, of similar size or similar shape, you can say. So in that case, 2 into, we can write 2 into Ixx by Ixx plus AH square. After that, the moment of inertia for the wave part, for the middle part. Okay, first of all, we need moment of inertia for these two, as these the dimension are same, so it will be 2 into Ixx plus AH square, sorry, AH square plus moment of inertia of this mid portion. Now for this mid portion, it is in the neutral axis, or the axis is in the center of this particular area, right? So it will be BD cube by 12. Okay, you can see the formula here, plus BD cube by 12. Now here the B is nothing but the TW, thickness of the shear wall, and LW, which is length of the shear wall. Okay, BD cube by 12. So this is how we can find, the moment of inertia, and from moment of inertia we can get the Z value, I by LSW by 2. LSW by 2 means the distance of the extreme fiber from the axis that we have considered. Okay, so after that we need to find the stress, the maximum stress we have got, area we have, so obviously PU by A. Okay, so we need to find out the stress plus MU by Z. Okay, so the stress we have got F max, that is the stress max, we have got 14.07. But what is our limit? Our limit is 0.2 FCK. In our case, as the FCK is 35, so it is 7. So you can see the result is matching with ETABS, right? Yes, 4512, 8599, right. We have given this only. 451. Okay, sorry. 4512, right? Let me see. Okay, 451. Sorry. Thank you for letting me know. 4512. Fine. Yes. So now you can see the stress has increased to 14.59. Yes. Okay. So I hope it is clear to all of you up to this. I hope it is clear to all of you. Okay. So now what we need to do, we have got this, that we need to design these areas for the boundary limit. Okay, as it is greater than, the stress is greater than the limit, which is 0.2 FCK. So now what we need to do, we need to find the moment on this wave. So for that we need to find the load on this wave, and also the moments or the loads on this particular boundary elements. Okay, means we need to divide this. So to find the load on the wave, what we can do, simple method, load on the wave will be load by total area. Total area means area of the wave. What will be the area of the wave? This one. So the total one is 2310. So you can see the middle part, from both the sides we have got 450 like this. The middle part will be 41510, and this thickness, actually in our case it is a rectangular shape like this. So here this bulb will not be there. Okay, so 300 and 300. So thickness of this boundary element and thickness of our wave part or the middle portion is same in our case. Okay, so you can understand what is the area of this particular part. 1410 multiplied by 300. Okay, this is the area of wave. So if you see here the method, the formula, so this is a simple formula, you can find it. load by total area multiplied by wave area, right? So we'll be getting the load on the wave area only, load on the wave area only. Okay, so what we need to do here, if you see, we have got tension and compression, right? So ultimately what we need to do, so what it will be, let me write it here properly, just give me 1 second. What it will be, so the net moment, how we are going to get net moment? The net moment will be mu33 we have got from ETABS minus how we gonna find, sorry, not net moment, this is the moment, this will be the moment at the wave, or you can say the mid part, mu33 minus what I am doing, sorry, let me write from the beginning. If I want to find the moment of the wave portion, because we need to deduct this particular moment, right, from the moment capacity of this two. Okay, so for this we need to find the moment of the mid portion. It will be the total moment mu33 minus, okay, fine, it will be what it will be, tension and compression, right? What it will be, it will be moment at the middle, right, yes. Okay, this is the first method. We need to find moment at the total moment minus moment of the middle, then we will be getting the moment capacity of these two, these boundary elements. Now how to find this moment of the middle? We will be finding the moment of the middle using the method that we have used for the flexural design. Okay, we have used for the flexural design, right? What we have done, we used IS 13920 NX A. We have used IS 13920 NX A. So now using this method, using these formulas, you can find the moment of the mid portion. Okay, and you need to deduct this moment from the moment for the total area, the total shear one, right? Then only we will be getting moment for this particular boundary elements, two boundary elements, right? So this is what we have done, I guess. Let me see. Yeah, it is written that the moment carrying capacity by the boundary element will be the total moment of the shear wall as a whole minus moment carrying capacity by the wave portion. Okay, is it clear? Is it clear? So now if you see, these are the methods that we have explained in the previous lesson. Let me show you here. IS 13920 NXA. So where it is? Yeah, here. IS 13920 NXA, moment of resistance for rectangular shear wall section. In that case, we have two processes. We need to check whether our shear wall is satisfying this particular criteria or this particular criteria. So after that, if it is satisfying this criteria, then we need to find the moment, this mu, from using this method, and otherwise we need to find the mu using this method. Okay, so we have created both the methods. In our previous lesson also, I have totally explained this process, right? So similarly, we will be doing this here to find the moment of the mid portion. If you see here, we have these values: lambda, phi, beta, xu by lw and xu star by lw. What are the things I have explained in the previous session? Please do watch the previous session to find out these things. Then we have calculated the mu from here. So this is the mu we have got for the mid portion. Okay, and this is the mu we have got from ETABS. So this mu is for the total, and this mu is for the only wave portion, right? Now if I deduct this particular mu or this particular moment from the total value, what will happen? We will be finding the moment. We will be finding the moment for this boundary elements. For this boundary elements, right? Now, for this boundary elements, what we have done? What we need to do? We need to find this tension and compressive force, because we will be designing the boundary elements for the compression, right, as per the IS 13920. So we need to find this compression and tension, this force value. So if you see the moment, this particular area will be tension or compression multiplied by lever arm. What is lever arm? How are we going to find this? Lever arm is nothing but, here we have the tension, we have the compression. So distance between these two forces will be our lever arm, right? We have got, if we have two opposite direction forces, and here we've got the center point. So the distance between these two forces, this is our lever arm. This is F1, this is also F1, but this is negative maybe. Okay, here we have tension upwards, compression downwards. So these two opposite direction forces, and the distance between these two forces, we have got the lever arm. So the tension or compression, whatever it is, multiplied by lever arm, will be getting the moment, right? So here you can see we have used the same formula. From that we will be finding the T or C, moment, tension or compression. Okay, now in both the cases, the amount of compression we will be having in this particular zone, the same amount of tension we will be having in this particular zone. So here you can see the T or C is equal to mu by lever arm, So we will be finding the T or C value. Okay, so here you can see the net force of this area. Now this is for case 1. Now case 2. Now we need to see whether it is meeting the case 1 or case 2. Okay, here you can see this one. We need to set a check. In our case, what is this value? Ultimately, here you can see the XU by LW is 0.5101 and XU star by LW is 0.456. If it says that if the XU by LW is less than XU star by LW, then only we can use the case 1. Okay, as per the Annex A of IS 13920. But in our case it is different. So we cannot use the case 1, that means the first method. So we need to go for the second method. Okay, so using this second method we will be finding the moment. So we have got this moment for the wave portion, and then from the total moment, we will be deducting, for the total moment we will be deducting the moment of the wave. So we have got the moment for the boundary elements. So now from this, using this moment, we can find the tension or compression for both the boundary elements. So you can see here, this is the tension or compression. Okay, so now you can see like Siddiqui sir has made this Excel sheet very amazingly. You can see it is saying you totally that you need to use the case 2. So these are the formulas, or you can say interlinks. You just have to put here the what it says, the relations. Just have to put in the Excel, and it will be showing you that whether this criteria is meeting and which criteria you need to use. So this is also not required. You can check manually also which criteria is meeting, and you can use the criteria for this. Okay, so now we have got what we have got. We have got the tension and we have got the compression, which is here 237.287. Now what I have explained previously, we have this axial force PU, maybe PU2, PU1. We have here tension, we have here compression, TC. So what will the net force here? PU minus T. And what will the net force here? It will be PU plus T. Sorry, PU plus C. So you can see here, for one case we have PU plus T, sorry, minus T. So we are getting 641.84 kilonewton total force. This is not needed. For the other side, we are getting the net force, which is sorry, 1116.42. So this is because of PU and again compression. So it will be in the same direction. So add addition. So this is the one we need to use. So this is the value we will be using. Right. So what we have got? We have got the net force. Okay, net force. So net force as we have got, so we can easily use the formula PU is equal to 0.8 times 0.6 FCK AC plus 0.67 FY ASC. Now how to find this area of concrete? Obviously we have the boundary element of 450 by 300, right? We have got this. Now what we need to do, you need to assume some reinforcement area first. Okay, we need to assume some reinforcement area, maybe 1.5% we need to assume. Maybe we are assuming 1.5% at the initial. So what it will be, 1.5 by 100 multiplied by 450 by 300. So some value you will be getting. So this is the area of reinforcement. Okay, so what it will be the gross area of concrete? It will be this particular area AC. Okay, so 450 by 300 minus this AC. So we'll be getting AAC. Sorry, what we have done, this is area of steel, right? So this is our ASC, not concrete. This is ASC, and this will be the AC will be the total area of concrete minus the area of steel. So we'll be getting the gross area. Sorry, not gross area, the left of the total concrete area, exact concrete area, right? So these things I don't have to explain actually. It's very common thing. So here you can see what we have done. Let's assume some reinforcement percentage here. Let's assume 1.5% as we have said. Okay, so if we use the 1.5%, so from there we can get the moment carrying capacity. How we are getting this moment carrying capacity? Can anyone tell me? Can anyone tell me how you are getting this moment carrying capacity? You just have to check that this is the capacity we need. See whether it is greater than this one or less than this one. Okay, we need to check whether this is greater than this one or less than this one. Okay, so here you can see it is G104, this one. So using this formula, you can see load carrying capacity of the boundary element, this formula 0.80, this formula that I have explained just now for the compression design of short column. Okay, so here we are getting the total PU value is 1527.31, but the PU value, the total force we have got 116.42. That means our shear wall or our boundary element is capable of taking, capacity means capable of taking this amount of force. But in our case, this is the force that we are getting. Okay, so that obviously this is greater than this one, the required one. So we can go with 1.5%. Then you can reduce also. Let us reduce this one. Let's see 1.2%. Here also we are getting less, maybe let's see 0.9%. You can see we are getting very less reinforcement. Let's go with 0.9% only. So here if we use, or maybe 1%, let's use, because in shear walls let's not use very less reinforcement. Let's go with 0.8% is the lowest one, right? So let's go with 1% only. So if we use 1%, here we are getting 1522.21. This is the net force using the short column method. Okay, required is 1116.42. So obviously okay. Now we just have to assume some rebars. Okay, 1% of the boundary element. We have considered 1% of 450 by 300 reinforcement. Okay, so now you can easily get the reinforcement area, and you can use this reinforcement area for finding out what are the bars you need to use. So suppose I'm going to consider, maybe let us keep 12 mm rebar, 40 mm clear cover, and the stirrup. Here I am not designing the shear reinforcement. Okay, so let us keep shear the stirrup diab as 8 mm only. So now here what is it saying? The required is 12 number of bars, 12 mm diab, 12 number of bars. Now see, we have 450 by 450 by 450, 450 by 300. Now providing 12 number of bars, that means maybe 4, it will be very clumsy, right? So let's not go with 12 mm. Let's increase it to 16 mm. Let's increase it to 16 mm now. 16 mm, enter. Now it is saying 7 number of bars, 16 mm dia we can use. Okay, how you can find this 7 number and which mm dia? I have explained in the previous video. A simple method, just you have to find the area of the bar and divide it by the required area. That's it. Or divide by the area that you are providing. That's it. So you'll be finding the number of rivers. Now here it is not possible to provide 7 number of bars, because it is always recommended to provide similar reinforcements in both the sides, right? 7 number of bars, how are you going to provide? In one direction, 1 bar, it is not appropriate, right? So what you can do, now here you can write by yourself. Now this is totally up to you, just for your understanding. We'll provide 8 number of bars instead of 7. That means 4 in this side. The drawing will be 4 in this particular side and 4 in the other side. So we have got this one. I hope it is clear to all of you. Okay, so we have found out that for the boundary elements, we need to provide 8 number of reinforcements in both the sides, not in single side. Okay, for both the sides, 4 there, 4 there in the other side. Okay, so 8 number of reinforcement for the boundary elements. So this is how we can design the boundary elements from the result of the ETABS. Very easy, right? This is the first time. It might be, it looks like very confusing, but once you follow the method again, and you do by yourself using the formulas given in the code, you can easily get this, and you can create your sheet also, calculation sheet also. Okay, so now what I'll do very fastly, I'll create a section in the section designer in ETABS. I'll assign this here in the shear wall, and I'll check what is the DC ratio, that means demand per capacity ratio. Okay, whether our design is correct or not, because we need to check whether the DC ratio is crossing 1 or not. Okay, so let's go to shear wall design and define general PR sections. For that, let's check what is the shear PR section number for us. Let us right click on the PR, and it is PR section P9. Okay, fine. So now I'll go to general reinforcement sections, define, add PR section. Here we'll be using M35. Here you do not have to name it. If you want, you can name it afterwards also. Let me go to here. I am not going to create a new one. I'll be assigning the PR section to the existing one, right? So here I'll go to P9. From P9 I'll be creating, right? P9 story. At the bottom story I have taken, so parking 1, this is the story name actually. From here I'll go to section designer. So click on OK, and it will redirect you to section design. Okay, so this is your section. Is it the correct one? Let me see. No, this is not the correct one. Oh, okay, we have selected P1, not P1, we need P9. Okay, yeah. So here we have got this P9 2310 by 300 mm shear bar. Okay, so some reinforcements are provided. What I'll do, I'll delete these reinforcements first. So click here, right click here, and I'll make reinforcement as no. Initially I do not need this. Click on OK. Shape name, okay, let me give a shape name, maybe section For P9 we'll be providing maybe section 1. Click on OK. So now we do not have any reinforcement here. Now let us create some reference lines so that it will be easy for us to create. Let me go to here, draw reference shape, draw reference line. So from here to here I'll create, let me cancel it, reference lines, draw snap option. Let me snap the grids also. Okay, so from here to here I'll be creating one reference line. Now I'll replicate. Okay, so how to replicate? You just have to select this and edit similarly as we used to do for the ETABS. Okay, now along the X direction you can see 450 mm our boundary element. So I'll create the half first. It will be 225. Number maybe 2 because we need 450 mm up to the end. So number 2. Okay, so you can see this is the total boundary element distance 450 mm, and here we have got the center line. Okay, similarly we'll do from here. So let's draw from here. You can also copy from here also, your wish. Let's draw one at this particular end. Okay, here we do not have this, so let me select this line again, edit, replicate. It will be minus 225 2. So you have got this reference lines, you can see. Now I'll draw a center line here. Okay, center line here. For that let me go to edit and draw snap options, draw snap option. Here let me see if we have midpoints here, line ends and midpoints. Okay, now I'll take a line here again. This is totally your approach. There are different methods to do this. See, we have this midline. So let's draw this midline up to. Okay, we have created, what we have done, we have just created a reference area. Okay, now again I'll copy this, replicate this, edit, replicate. Previously I hope you remember that for the flexural design, the distance between the reinforcement means the center to center distance we have got 135 mm. Okay, so here I'll create one line for 135 mm, just one line, and click on OK. Here also for this I'll be creating one, edit, replicate, minus. I'll explain what I have done actually. See, this is the boundary element area. I'll be assigning the boundary element, and from this line to this line we'll be providing the flexural reinforcement. Okay, so again for the clear cover also we need some reinforcement, reference lines. So what I'll do, I'll draw a line here and I'll draw a line here. Sorry. Okay, now let me turn off this. Let me replicate this again. Okay. Edit, replicate. Now it will be along y direction plus 40 mm. Okay, and the other one, replicate, it will be minus 40 mm. Okay, so yeah, we are done. Now what we will do, we'll go to reinforcement. Here you can see draw rebar shape. I'll take this, draw rectangular rebar, and I'll draw one here at this midpoint. Let me just turn off this one, maybe snap to line intersections. Let me turn off this. Now here we have this intersection point, right? So escape, rebar. Here we have draw rectangular rebar, so I'll click here, and after that here also we'll create one. So here we have created the boundary elements. Now we will edit this. Just right click at this point, and here you have got the total property of the boundary. Let us change it to HOSD 500. This location we have already given, so we do not have to provide this. Okay. Height, in our case, height will be 300 minus 40, right? 80. So what will be the height? 300 minus 80, because from both the sides we have 40 mm cover, and the width will be 450, right? So 450 minus, what you can do, 450 minus 40, right? So 450 minus 80, both the sides. Okay. Now tie bar, we want 8 mm bar. Corner bar, these are the corner bars, actually 4 corner bars. Okay, so we will consider only 16. Corner bar 2, 16. Sorry, 16. Corner bar 3. Can ETABS provide boundary design, or it have to design manually? No, ETABS will only provide you the boundary needed or not, what is the boundary length, what are the force and moment. Okay, that's why I'm explaining, right? If ETABS is giving, there is no point of doing all these things. So yeah, we have provided 4 corners, 16 mm bar. Now in between, see, this is the first length, edge bar. Okay, edge bar one means this top one. So in top one, if you see here, the bar size will be 16, and the number of bar, already 2 corners we have provided 2. So in whole direction we need 4, right? So in between we need 2. The spacing will be adjusted automatically, you can see here. So the edge bar 1 completed. Now in this direction we do not need any, so just make it 0, the number of bar. Okay, now in the edge 3 is the bottom one, so in bottom one also we need 2 number of bars of 16 mm. I hope you are it is clear to you. This edge bar means the bar at the middle portion. Corners we have provided already, so we need total 4 corners. We have provided 2, in between we will be providing 2. Okay, now edge 4 means this one, so here we do not need any reinforcement, so make it 0. Doesn't matter what is the reinforcement area, so sorry, the bar area. So now let us click on OK. Click on OK, and you can see it has automatically adjusted, right? So now we will do the same here. I think what we need to do, we do not need these lines actually. From the very edge only we can provide, we can start providing the reinforcement, right? So we do not need this. Okay, no, not an issue. Now we'll do the same for this. Otherwise you can also replicate this to this particular end. Okay, it is also possible. Let us delete this and replicate this. So what will be the length? 2310 minus 450. What is the length? 2310 minus 450. It will be 1860, right? So let's select this, edit, replicate. Along x direction, y will be 0. Along x direction will be 1860. Okay, yeah. So there is no need of creating. So these lines actually we do not need. We can directly start providing from this edge only, right? For the flexural reinforcement. So let us provide this flexural reinforcement. If you see my previous video, we have found out for the flexural reinforcement we will be providing T16 means 16 mm dia bar at 135 mm center to center, right? So now what we will do, we'll take a strip of reinforcement in here. You can see here we have this draw line rebar. So from here to this point, similarly from here, sorry, let me select it again, from here to this point. Okay, now let's adjust this. Right click, you can see what it is, change it to 500. Okay, so location we do not need, we just have to change the bar size, it will be 16, and the maximum bar spacing will be providing 135 mm. Okay, click on OK. You can see it has adjusted this. Now similarly we'll provide here, we will provide this bar size 16, and the maximum reinforcement spacing will be providing 35 mm. Okay, right? So now these reference lines are not needed, so you can always delete these reference lines. Okay, if we have select, not have any option, let's delete this. This also, we have here one, sorry, delete, here also one. Even it is not an issue because this is just a reference line to show you. Yeah, so we have created this section here from the design, and we'll be checking whether the design that we have done using our process, whether it is okay or not, right? So let me click on OK and click on OK. We have created this PR 1. Okay, click on OK, select this PR, go to here, shear wall design, assign PR section, general reinforcing. We have this PR 1 and PR 1, top and bottom, both the directions, and we do not want to design because already we have designed, so we want to check. So reinforcement to be checked, and click on OK. Okay, so what we can do actually, let us assign to all the stories rather assigning it to one single story. Okay, because we have designed for the maximum one. Let's assign it to all the stories. Assign PR sections, general reinforcing, PR 1. Fine. Now let's run the design. Okay, now let's check the DC ratio, display design info, and here you can see PR DC ratio, demand per capacity ratio. Apply. Here you can see it is 0.9, 0.8, and if you, as you go above, it will be reducing to 0.7, 0.6 like this. You can see 0.8, 0.5, 0.3. 0.3 means very less, right? 0.4. So in that case, in this particular shear walls, you can reduce the reinforcement. You can reduce the reinforcement in this case. So you can check the moment here, and you can design it separately again. Okay, 0.4. Otherwise, you can keep it same. Otherwise, maybe some, as it is a tall building, you can change. But in normal small buildings like G+5, G+6, that case you can keep it the similar one. Okay, so I hope it is clear to all of you how we can design the boundary element and also the shear wall, the flexural design, using the method that I have explained in the previous lesson, live lesson. Today I have explained the boundary element. So the total shear wall is completed. Again, I have also showed how you can use this design results to the section designer, and you can check whether the design that you have done manually, whether it is okay or not, right? So I hope it is clear to all of you. If you have any question or any query regarding this, please do ask me in the comment. Let us take some questions. Let us take some questions. Yeah, so what I was saying, yeah, we'll be launching the SAFE course very soon actually, Mr. Srinivas, and you'll get to know. In case of L-shaped shear wall, what will be the possible boundary zone? No, in case of L-shaped shear wall, you will not be designing the shear wall for the total L shape, right? You will not consider this as a whole PR. It will be PR 1, it will be PR 2. So again, you will be designing this as a 1 PR, and you will be designing this as a 1 PR. So here, yeah, there might be, you will be getting higher reinforcement from both the sides. This is the boundary element. Even boundary element is not always required. If it is crossing 0.2 FCK, then only. If it is required, then yeah, similarly you will be designing this particularly single using this separately, and in this particular area you will be getting a you can say combined result. So you will see the higher reinforcement you will be finding. Maybe we cannot see, we just have to compare P2 and P1. Wherever you are getting the higher one, you need to provide it here. C shape, T shape, whatever shape it is, you just have to break it down in single pairs, right? Suppose this is my C shape, so it will be P1, P2, P3. If you have a combined like this, 2-3 sections like this, so P1, P2, P3, P4, P5 like this. So every single pair will be designed separately. Okay, now you just have to check what is the moment for all the, suppose these 3 shear walls are having similar moments, maybe plus minus some 5-10 kilometers per meter, kilometer or something like that. In that case, you can go with the higher one and you can provide the similar reinforcement for both the 3. You can check for these 2 and you can assign the maximum one to the both the ones. Okay, sometimes you need to go for the value engineering also. That is a different thing. Okay, any other question? How to calculate time period for shear wall building? Time period for shear wall building depends. If you are considering it as a dual system, there in IS 1893 you have the formula. Okay, and normally if you are considering it, suppose a frame, moment frame, even if you have a core wall, most of the moments are taken by the column. If you are considering it like that, then you can go with the 0.09 h root under d. That is a different topic. We'll discuss this in different session. Okay, so in the description you will find our Telegram group link. You can join there, and our mobile application also, Illustraca, which is available in the Play Store for the Android users. So you can download our app also. In that you will be finding different courses for basic to advanced ETABS, course for the site engineering. Total 87 videos will be there for the site engineering course. So sitting at the home, you will be learning the site engineering actually, like what are the site aspects of a site, what are the things happening in the site. So for the professionals, it may not be needed, uh, but for the students, even if you're a professional, maybe you are working in the design field mostly, not in the site. So you need to get some idea about the site. So from that course, very like easily you can get everything from the bar bending schedule, reinforcement, provision of reinforcements, what are the excavations, how excavations are done, how foundations are done, beams are done, columns are done. Everything in that course explained by Mr. Akshay Kamath actually. So you can get this site engineering course also. Then ETABS course, we have 3 ETABS courses. Now we have the bridge engineering course also. Okay, the ongoing course is the bridge superstructure. Uh, uh, in few days we will be launching the bridge substructure course also. You can join there. We have the AutoCAD course for the students and professionals. Okay, so even we have the Photoshop course, because sometimes we need some graphical representation to the client, so we need to use the Photoshop. So we have the Photoshop course also. These will be live classes and recorded also. So whatever you need, you will be getting there in our application. And very soon, maybe by 2-3 maybe 1-2 weeks, we'll be launching BIM structure. That means I will be using the building information modeling for the structural detailing, RCC and steel also using Revit. So we'll be launching this course very soon, and a very prominent engineer will be teaching you on this course. Okay, what will the limit of our DC ratio? 1, obviously. See, your demand is suppose 50, your capacity is 50, so you'll be getting the DC ratio as 1. Now your demand is 100, your capacity is 50, you will be getting DC ratio is 2. So obviously this DC ratio 2 is not required because our capacity should be more than the demand. Okay. These are simple questions, Mahesh. How to calculate the. In previous lecture, we have designed flexor for total width. See, just once check what is the, let me show you. Yeah, I thought that, see here, though we have designed for the total depth, let's check what is the force that we have considered, where it is flexural design. Yeah, here. So this is the force 794. Okay, this is the PU and this is the moment 1930 that we have used. But here you can see what is the force PU. We have used 4512. This is the moment 2155. That means this PU that you have considered here for the flexural design, it is already distributed. Okay, they have already done distribution. They have divided it into 3 parts and they have given you the moment which is required for the flexural design, or the PU value for the flexural design. Okay, so there is no need. This is the total axial load, and here you are getting the axial load which is required for the mid part only, because here the requirement of boundary element was there. Okay, the places where you do not need boundary element, you will see that the PU will be somewhat more here. Okay, able to join Telegram now. Why? You can join this group. We have, I think you do not have Telegram application in your mobile. Please do download the Telegram application and you can join the group actually. Yeah, 16 number of reinforcement inclusion the right, and yeah, previously we have not considered this boundary element, though it was there. Just to show you. Okay, so for the mid part, the similar reinforcement will be provided, right? So here we didn't, if when we have we are creating the section designer in the section in the section designer, there we have used the spacing only, not the number of bar. We have used only the 135 mm spacing. So for the mid portion, whatever number reinforcement is there, it has created automatically. Okay, I hope it is clear to all of you. Previously also this boundary element was there. Just to show you the method, I have used this value. I have not taken any other wall and just done the flexural design. Okay, so you need to follow the same process actually. Just find out what are the reinforcement, what is the spacing, and then again for the boundary element also, what is the reinforcement, what is the number of reinforcement or spacing. Okay, and provide it here. Okay, so it's been a great session with all of you. It's almost one and a half hour, right? So I hope, yeah, the previous session has have got a tremendous you can say response from all of you guys. I'm really thankful to all of you. I'll always try to create such contents for all of you free of cost. We have paid courses, but still along with this, see, the students who are taking classes from me in my paid courses, they will be also learning the similar process. There is no other process, right? So this is the similar process. So here I'll be posting contents in my YouTube videos also and in my paid contents also. Yeah, in the paid courses, the total scenario I used to explain from the very beginning, right? That is the difference. Otherwise, if you want to learn the specific things, you can learn from my YouTube channel also. So do subscribe and do stay tuned with us in our YouTube also. I'll be creating contents like that, some important contents. I will not create contents like how to create model, maybe foundation in the ETABS. Those things are not required, right? What our requirement is that while working on the field, we are facing so many problems, right? So those problems need to be solved, and someone should have, like, there are so many paid contents. So yeah, from the paid contents you may get, but you do not know what they are going to give or what I am going to give you, right? So from the YouTube channel, if they are providing you, I am providing you these things, these contents, these required contents. So obviously you will be there for me. You may not be taking my paid course, doesn't matter, but you will be getting the content in my channel. That is my promise. Okay, that is my promise. Okay, so I'll be signing off now. I'll be ending this session for today. I hope all of you have enjoyed this session, and if you're a new in my channel, please do subscribe this channel, share to your friends, so that all of your friends and colleagues can get such contents, and they can also learn. If they have, maybe they are aware of these things, but still do share. If someone is needed, it will be helpful for them. Okay, so thank you all of you for being there for this 1.5 hour with me, and thanks for your support. I hope this video will also get your support and love like that you have shown in my previous video. And again, thank you so much. So I'm signing off. Good night.